for question 5. So this is find a constant b such that h is continuous at x equals 2. And by the way, this is question 57. Please move the application away. It's not on the shared application. Okay, whatever Zoom. So this is question 57 in those chapter exercises. How do you do this? So you basically, you're focusing on x equals 2, right? Find a constant b so that h is continuous at x equals 2. So what does it mean to be continuous? So you're continuous at x equals 2 if your limit as x goes to 2 is equal to h of 2. But in this case, you've got different formulas depending on whether x is bigger than 2 or less than 2. So you'll need to take left and right hand limits and just compare what you get and choose a number b to make the two limits equal. So if h is continuous at x equals 2, then the left and right hand limits will have to be the same. And of course, both need to exist. So left hand limit, use b minus x squared. So plug in 2, b minus 4 for the right hand limit. Use x plus 1. Plug in 2 to get 3. So b minus 4 equals 3. Choose b equals 7. So now the second part of the equation says look at x plus 1 and look at 7 minus x squared. And find all points of continuity. And automatically, you know that it's continuous at 2 because you just showed that. X plus 1 is certainly continuous on its domain, so that's negative 2 to 2. You're continuous all those places. 7 minus x squared is certainly continuous for x bigger than 2, certainly continuous for x less than 2. The only point left to check is x equal to negative 2. So we have to make sure we check that. So that's what I'm doing here in my next part. And notice this solution by its nature sort of requires more explanation, and you're seeing me give that clear explanation. Given this choice, note that x plus 1 and 7 minus x squared are both continuous, and h is continuous at x equals 2. So the only possible discontinuity remaining occurs when x equals negative 2, and let's check that out. So I just do the left and right hand limits and observe that they're different, which shows that h is discontinuous at x equals negative 2, and therefore it's continuous at every other point. So it's continuous on the interval from negative infinity to negative 2, and on the interval from negative 2 to infinity. Pause briefly for any questions on that one. Question 6. So what are the horizontal asymptotes? The possibilities for horizontal asymptotes are the limit as x goes to infinity and the limit as x goes to negative infinity. You'll see me state that. And that is something that I asked for in the rubric too. Like I asked you to tell me that you know like what it is you're looking for. Like find the horizontal asymptotes. Okay, well this is what they are, and let me show you how to find them. And you could have phrased that like in your own personal style, but I'm looking to see that you know what an asymptote is, and that you're doing the correct calculation. So both of those limits, both to infinity and negative infinity. I mean, you know immediately that it's going to be, you respond to a question. Yeah, so I hope you're not minding if I'm answering these direct message questions in person, not identifying who asked. But they're good questions and worth everybody hearing the solutions. And so this question is saying like I notice you're explaining everything you're doing, and the issue is like when you're under time pressure on an exam, it's going to be difficult to explain like everything like in detail, like and have enough time to get the right answer. And what I always did for so first of all, what happened to my screen share? I do have some advice for this, but I've managed to. Okay, so here we go. I do have some advice for this. Like there's two levels, right? So the first level is, calculating and getting what answer you want. So that's first, and then if it takes the full test time to do that, then do that, and don't worry about as much as the explanations, and then just take the hit on the written communication. But as you get more experience, you're going to be wanting to shoot for written communication as well. And so, like, what are some tips to be able to do that? What I always do when I'm taking a test is, like, I have the test paper, the stuff I'm going to turn in, and I also have paper beside me that I call scratch paper, that I use for just doing calculations or work or whatever. So what I'll do when I'm solving a test is on my scratch paper, I'll rapidly write out calculations, I'll scratch things through, I'll make mistakes, I'll cross them out, I'll do whatever it takes to calculate the solution and then basically solve the problem. And only after I've done that will I start writing my solution that I'm going to show to the instructor. You might think it would waste time to do that because you're basically doing things twice, but the point is, when you're working on scratch paper, you don't need to explain anything to anyone. You just need to write down stuff that like you can understand for yourself. And once you get that done and you've got it figured out, then you can say, okay, now I can think about what I'm going to write to the instructor to explain myself. So to me, like this issue of this idea of like using the scratch paper first has been super helpful, because if I feel like I got so much anxiety when an instructor gave me a test that was just a test booklet and I had to write everything in there, because I feel like any mistake I make, it's just there forever, or I have to spend 5 minutes like erasing or, furiously erasing or whatever. But with the scratch work that I know I'm not going to turn in, I'm free to write whatever I want. I'm not going to be embarrassed. I can throw it away afterwards. It's helps me out. It's a little bit of a tangent there. No pun intended. And for question 6, so you can kind of look at this and know that the answer is going to work out to 9/2. But it sort of speaks to what we were talking about, because you don't want to just write down 9/2. You want to explain, I know what an asymptote is, and you want to show you can do the calculation. And if you just plug in x equals 0, you'll get indeterminate form, so it'll bug out on you. But like what you can do instead is show that you can divide through by x squared, and then here you see me going from here to there without any comment, because that's fine, because at this point I didn't ask you to show every step with the limit law, but so you don't need to. But what you're doing instead is just setting it up so that a reasonable observer could know that when you go from here to here, yeah, you're using the limit law, you're breaking it up into numerator and denominator. And yeah, we all know that 4 over x squared, that's going to 0 as x is going to infinity, because numerator's staying constant and denominator is getting large without bound, so the whole expression is going to 0. So like this division by x squared trick is really good, and then you kind of keep on going without comment. So that just shows you sort of like the different levels of explanation. Like if I definitely asked you about showing your steps with limits, then, well, yeah, you'd want to focus on that. But here you weren't being asked about that. You're focusing instead on horizontal asymptotes. And definitely I showed you the calculation of the limit. I didn't try to compute an indeterminate form. I did the algebra to get rid of it. But I didn't spend any extra time on limit laws when I didn't have to. And here I even still wrote it down, even though it's not, even though it's the same calculation, just showing you that you get the same answer. And that's because x squared will take the negative numbers and make them positive. Doesn't change anything. So there's only one asymptote, and it's y equals 9/2. And I actually made a conclusion. Like I didn't just write down this limit is 9/2. I wrote down because of that, here's a formula for the horizontal line, which is, you know, it's a nice thing to do, and it doesn't take much time. For extra credit, by all means, skip it. You don't have to do this, but this is from the section 2.9 on the epsilon delta argument, and so you solve it like the way that we solved it in class that time. But I probably won't spend too much time on this because it's not required to do the class. It's just enrichment to make sure, like, at least you've been presented the epsilon delta definition and have a chance to work with it. And if you're interested in it, then by all means get some extra credit, and you'll see us work with this stuff more in higher math courses. But basically the elements were choosing epsilon, choosing delta, and then showing that choice of delta worked. And because it's extra credit, I don't really give much partial credit. So it's just like whether you're trekking through this proof and then you're getting credit or not, and you're not. Which feels a little unfair because there were some great proofs of this, but if it wasn't this rigorous epsilon delta thing, then I didn't give credit. Just because it's extra credit, specifically looking at the epsilon delta stuff. That's all. I know that I spent a lot of time on that, but I hope that it was worth it, because I hope that sort of getting on the same page, like in terms of expectations, is worth it. I think a lot of times with calculus, it's not so much the calculus, it's a mismatch of expectations versus like what we're giving, and I think that's partly on the instructors. I think instructors don't always set expectations that well, and then that can lead to like negative situations, which is no good. So that's why I wanted to spend some time on this. But I also wanted to spend some time like doing some of these like chapter review exercises. I think I pulled basically every single test question from chapter review exercises. I identified 3 of them, but I think there's even like a couple more. Like if you're with me on page 119, like number 18 was also a test question. So I guess the moral of the story is, like, the more practice you do from chapter review, the more likely you'll like land on something just by chance. But let's do something. I'm gonna do number 43. So it's a limit problem. And I don't like my test to be just like something you've seen exactly before and you're just plugging in numbers that are different from the practice problem. I do like a little bit of new challenge to come in there. So I think number 43 is a great example for this. So go ahead and start on it if you've got the book, otherwise I'll write it down. Okay, so you're on a test on Wednesday and you see this problem. What are you going to do? We've got like 12 minutes left. So instead of giving you 5 minutes to work, I'll give you like 30 seconds. Think, what would you do? Like, what's your strategy for doing this? And then I'll say some words. Okay, so after letting you think about your strategy for a second, I encourage you to do this on the test as well. Like, when you see that problem for the first time, just give yourself a minute to think about your strategy or how you want to approach it. Because if you immediately just try to dive in and expand this or cancel that, you might get nervous and you might trap yourself into a way of thinking that's not so helpful. So there's two things that I see. First of all, if I just try to plug in x equals 1, and this is limit from the right, so I'm only considering values of x that are bigger than 1, but like whatever, okay. That's just because of the square root, because you can only take square roots of positive values. So don't get upset by that. The first thing I notice is that, well, x squared minus 1 factors is x minus 1, x plus 1. So I have a factor of square root of x minus 1 appearing in both denominators, and that's good, because like if I just try to plug in x equals 1, I'll get 1 over 0 minus 1 over 0, which is indeterminate. Well, it's like a difference of I mean, it's indeterminate because 1 over 0 is going to go to infinity and plus or minus infinity. 1 over 0 is going to go to plus or minus infinity. And no, you definitely can't say infinity minus infinity is equal to 0. That doesn't work like that. So you are not going to get any traction by just plugging in a number. This limit may or may not exist, but we don't know anything about it just by trying to plug in 1. So what do? I guess one general theme that we've been seeing is try to make a proper fraction out of it. So try to express this difference as one fraction. And then this actually sort of suggests that and also helps you, because if I want a common denominator, one way to do it is to multiply these two things together. That's right. But another way to do it that's a little bit quicker like now that we've noticed this, is I could multiply this by square root of what? X plus 1? I can do that at the outset. You see, I just multiplied top and bottom by root x plus 1, so I didn't change the value of the expression. But now when I multiply these two together, that's square root of x plus 1 times x minus 1. So it's square root of x squared minus 1. And is this actually going to be helpful? Maybe, maybe not. Let's see. So let's put this over a single denominator now. Square root x plus 1 minus 1. Everything divided by square root of x squared minus 1. Now we'll check and see if it's still indeterminate. So if I plug in x equals 1, I get root 2 minus 1, which is, I don't know, like 0.47 or something like that, or like 1.7, or maybe it's like 1.4, but whatever, root 2 minus 1 is some constant. And then when I plug in x equals 1 here, I'm getting 0. And I'm going from the right, so I'm getting positive numbers that are going to 0. So actually, this is no longer indeterminate, because it's of the form constant over 0 when you plug in 1. And when you have something like that, you know this is going to plus infinity or minus infinity, as long as this is like positive or negative. And so here, this numerator is a positive number. I mean, root 2 is bigger than 1. And the denominator is a positive number because x is bigger than 1. And you're squaring it, so it stays bigger than 1. So you've got positive number over positive number going to 0. Putting that together, this limit is plus infinity. And so I think you need a sentence to explain that. So I'd say since like x plus 1 minus 1 goes to root 2 minus 1, and x squared minus 1 goes to 0. So I did that without any preparation or looking at it in advance, just to try to maybe give myself the test experience. Give myself a chance to mess up in front of all of you, which probably will happen eventually. And when I first saw this, yeah, I was expecting to get an actual answer, and I was a little surprised to learn that actually it diverges to plus infinity. But I was able to figure that out basically by putting it over a single denominator and realizing denominator staying constant. Excuse me, numerator staying constant, denominator going to 0. And even if you had found common denominator by multiplying root x minus 1 and root x squared minus 1 together, probably that still would have worked. So any questions or comments on that? Let's try to sneak in one more. Although one of the morals of today's story is practice these review exercises. I mean, now that you know my secret of just picking review exercises for a test, I'm not guaranteeing I'm going to keep on doing that, but I'll probably keep on doing it to at least some extent. Let's try 42. It's the prior problem. So this is limit as t goes to 0 sine squared t over t cubed. So you see this on an exam, what are you going to do? As usual, you pause and you just take a deep breath and just think for a minute. How do you want to approach it? Like, what comes to your mind? And so whenever I see something like this, I see the sine t and I see the t, I immediately think that limit sine t over t as t goes to 0 is equal to 1. I immediately think I'm going to use that. This because there aren't like that many, problems, limit problems out there, and that is a limit that we know, and the textbook authors are going to want to give me a chance to exploit that. So sine squared t, that's sine t times sine t. So yeah, in fact, I already know how this is going to go, because how do you want to group this? So sine squared t, I'm going to group this as sine squared t over t squared times 1 over t. And just to be 100% clear about what this notation means, this is limit t goes to 0 of sine of t over t squared times 1 over t. Right, sine squared t is sine t times sine t, and t squared is t times t. So like you can write this like that. And what you know is that you know that limit as t goes to 0 of this, by the limit law, that's equal to limit as t goes to 0 sine t over t squared. So this first factor is heading towards 1, because you know limit sine t over t is going to 0, is going to 1, excuse me. And limit law says that limit of this function times itself is the same thing as the limit of the function, and then times the limit of the function. This is the product limit law. So anyway, this part is going to 1, and this part is going to plus infinity if t is from the right, and negative infinity if t is from the left. So this limit does not exist. I wouldn't say that it goes to plus infinity. I wouldn't say that it goes to negative infinity, because depending on whether t is bigger than 0 or less than 0, will cause the quantity to be like positive or negative. But the steps here are figuring out how to rewrite it in terms of the thing that's we just happened to get 2 examples that didn't exist. But you rewrite it in terms of the thing that's definitely approaching a fixed number times the thing that's, that's definitely going to like plus or minus infinity. And so on my test, I'm probably going to write once again like one concluding sentence, like since limit as t goes to 0, 1 over t does not exist. So this is one of those things that you can just say, for 1 over x or 1 over x squared, we know that as the denominator goes to 0, the whole thing blows up. And limit t goes to 0 of this other thing we just calculated equals 1. And notice something I didn't do. I didn't apply a limit law here. I didn't assert that this limit excuse me, was the limit of sine t over t squared times the limit of 1 over t. I didn't assert that because you can't assert that when you can't use the product limit law when one of the products doesn't exist. The limit law only works when both limits exist, and then the product of the limit is the limit of the products. So I had to be a little bit careful in the way I explained it, to just note that, like, this part of the product is going to 1, this part of the product is going to plus or minus infinity, so therefore the product of those two things is going to plus or minus infinity. Okay. We respond to some questions. Yeah, that sounds right. That's a strategy that I used. So I agree with that. Shouldn't sine t over t equal to 1? Sine t over t equals what it is, but the limit of sine t over t as t goes to 0 is equal to 1. And I have been using that. It's not equal to 1 over t, but you'll notice that I have a factor of t cubed here, so t squared times t. I'm just factoring that out. So this is limiting towards 1. It's not equal to 1. This is limiting towards 1. And this is a limiting, going towards like plus or minus infinity. So I'm definitely not saying that sine t over t limits to 1 over t. Just trying to respond to all the questions. Yeah, how did you get the first 1 over t? That's because I'm writing t cubed is equal to t squared times t. So t squared times t is t cubed. And here I have sine squared. So I'm just breaking it off like this, just rewriting that algebraic expression. Okay. Be welcome to email me any other questions or pop by office hours today. Apologize for going 3 minutes over. And so I'll write another test based on the same review material and give that to you on Wednesday. So thank you, everybody. Have a great day.
Thank you.